Hello, in this video, I want to talk a little bit more about dot products. There's one very useful technique that we have with dot products that I wanted to explain, and that's the idea of projection. So let's get right to it. Okay, so there's actually two different types of projection, but the picture is the same. So uh, there's when we're working with geometry in 3 dimensions or even in 2 dimensions, a question that we frequently ask is how much of this vector is pointing in the same direction as another vector. So I want you to focus on this picture over here. And we might ask a question, how much of B is pointing in the direction of the vector A? And we call that the component of B along A. And how you kind of look at it is you kind of cast a perpendicular shadow from B towards A and then form this right triangle. Okay. And the shadow portion going in the same direction of A, that's the component that we're talking about. Okay. So how can we compute this? Well, look at this right triangle that we have here. With, let's say the angle theta is between vector B and A. And the length of the hypotenuse is the magnitude of B. And one thing we could write down, so what we want is this length right here. I'm going to call that x. Right? We know that cosine of theta is the ratio between the adjacent side, which is x, divided by the hypotenuse, which is the magnitude of B. Okay. Then we can multiply both sides of the equation with a magnitude of B. Okay. And then now what I'm going to do is I'm going to multiply and divide by the magnitude of A. Okay. Why did I do that? Well, if we multiply by magnitude of A, numerator is something that we know how to compute. So this was the second formula for the dot product between A and B. So I can write down the numerator just as a dot product. Okay. And we get the length of the shadow. That's the X in the picture. So what we just computed here is what's called the scalar component, the length of the shadow or the magnitude of the shadow. So this is the formula we use, and the book does not have a notation for it, but sometimes people write comp for component of B in the direction of A. Right? So you might kind of memorize this notation as B is casting shadow onto A. So A is kind of sitting beneath B. And in the formula too, there's the dot product, and which is on top of one of the vectors, and magnitude of A comes on the bottom. So kind of notation kind of suggests that maybe A should be on the bottom as well. At least that's kind of how I think about the formula. And so this is a very useful formula. But sometimes knowing the length is not enough. sometimes you want the shadow not as a length, but as a vector on its own. So instead of looking at this blue shadow, what if I want it as an arrow vector here? So we can do that. So what we want is a vector that's pointing in the same direction of A, but has the length of the same length as the shadow we just computed, right? So this is the formula that we have, B dot A over magnitude of A. That's the length. So what we could do is we can multiply that length by a unit vector that's pointing in the direction of A. So we just have to, we already have the magnitude. We just have to give it a direction towards A. So take this formula and multiply by unit vector in the direction of A. And the way to get that is take the vector A and divide by the magnitude of A. So if you divide out, if you divide by the length of A, you get the same vector pointing in the same direction, but with unit 1. So the length 1. And then if you multiply by the length of the shadow, you're going to get this green vector here. So it kind of get messy, but we have this formula that's circled in green and multiply by vector A and divide by another factor of magnitude of A. That comes on the bottom. So this is now squared. And this is the formula for the projection when you want it as a vector. And this book has a notation for, and a notation is similar. So we're going to write it as proj, as in projection of B onto A. Right? So B is casting a shadow on A, so that's how we're going to write it. And then the formula is a little bit more complicated, but basically what you're doing is you already found the length of the shadow. You just multiply by unit vector in the direction of A. Okay. I hope that made sense. We'll do an example problem or two in a second. And another useful thing that you might have is, well, once you know how much of B is pointing in the direction of A, you might have a secondary question of how much is perpendicular to A. Right? So kind of, if you take away the parts that's pointing towards A, you just get the perpendicular portion. Well, basically, all you have to do is just remove the projection from B there. So take the vector B and subtract the vector projection from that to get the orthogonal component. When I say orthogonal, I mean perpendicular part. So that's what this will compute. Okay, so let's kind of try it out. So let's have vector A and B, and then compute the component of B in the direction of A. Okay. So to do that, component of B in the direction of A. So we're gonna first take the dot product and divide by the magnitude of A. So if I take the dot product, I get 1 times 2 is 2, plus 2 times 0 is 0, plus 3 times negative 3 is negative 9, divided by magnitude of A, 1 squared plus 2 squared plus 3 squared. So negative 7 over root 14. Okay. That's the length of the shadow. If I want it as a vector, we already computed most of it. So we just have to multiply that by unit vector in direction of A. So So that's the length, and multiply by vector A divided by the length of A. We already computed that. That was square root of 14. And I have 2 square root of 14 on the bottom. So that will become negative 7 over 14, which will simplify down to negative 1/2. So I'm multiplying the negative 1/2 scalar to each of the 3 components. Okay, so that would be the vector projection. I hope that computation made sense. So when would you use something like this? So one place where this pops up a lot might be in physics. So let's say you have a box sitting on an incline. So here's the box and it weighs 10 pounds. So there's a weight vector that's kind of pointing towards center of Earth, like directly downward. And then let's say it's on an incline that's 30 degrees. Okay. So whenever something is pressing up on a ground, there's a normal force, which means like the ground is kind of pushing up at the box, so the box doesn't fall through the floor. But the normal force kind of points perpendicular to the ground. So there's some leftover force from the weight. It's kind of that's in the direction parallel to the ground. So the box is gonna start to slide down the incline. So let's see how much of the weight force is kind of in the direction of the incline. Okay, so here, the vector that I'm interested in is the weight force. So that points directly downward. So 0, comma, negative 10. And this is a 2-dimensional vector, right? Well, how much is it pointing in the direction of 30-degree incline? Let's see. Well, we can get vector pointing in like a 30-degree incline by just kind of looking at a vector that's created by cosine of 30 degrees and sine of 30 degrees, right? That would be a point on the unit circle that makes the angle of 30 degrees from the positive x-axis. And I guess 30 degrees is a nice angle. So cosine would be root 3 over 2. And sine of 30 degrees is going to be 1/2. All right. And then we're gonna, what we want is component, how much of this force is parallel to this vector. So here I just have to compute the length of the shadow. So B in the direction of A. So we take the dot product and divide by the magnitude. Okay, so if I take the dot product between these 2 vectors, let's see, I'm just gonna have negative 5 on the top because the x component is just zeroed out. And the magnitude of the vector A, so I just kind of chose a simple one where its length is 1 because it's on the unit circle. So negative 5 pounds. So negative because it's kind of, the reason why we got negative because is because the unit vector we chose was kind of pointing upward, up the incline, but the force is pointing in the opposite direction of that. So that's how the negative appeared. So it's accelerating down the incline as if you were pushing it down with 5 pounds of force. So that's how it's gonna go. I hope that made sense. There's gonna be other homework problems kind of like this, so you'll get to practice this. I hope that made sense. Okay, so this is where I want to end this video. I'll see you soon.